Hello class. In this module, we are going to be focusing on finding our change in enthalpy by using stoichiometry. And so we'll be taking a look at some thermochemical equations. Before we get there, I want to go over what an extensive property is and what an intensive property is. So an extensive property, it depends on the amount of material that is undergoing the reaction. So examples of extensive properties or other ones besides enthalpy would be length. So another example would be length. Now, let's contrast that with what an intensive property is. So an intensive property doesn't depend on the amount of the substance. So it doesn't depend on the amount. And examples for intensive properties or bulk properties would be color and temperature. So it's just a couple examples that I want to give so I can compare and contrast these. Now, an easy way to remember if what we're looking at is extensive or intensive is if you can double it, it's going to be extensive. So, for example, the length. If we double it, we will get twice the length. That makes sense, right? Or if we had mass, if we double the mass, we get 2 times the mass. So that's an extensive property. But what if we want to double the color? Well, that's not going to make much sense because we would just have twice the amount of color. No. So that's an easy way to tell the difference between an extensive and an intensive property. All right, so an easy way to find an enthalpy change for a reaction, or a good way, is through the thermochemical equation. So the thermochemical equation. So what's the difference between that and our normal equations? Well, all that we're going to do now is we're going to put the amount of energy with the reaction. So here, we're going to say our delta H is going to equal 572 kilojoules for this reaction. So this is the decomposition of water into 2 moles of hydrogen and 1 mole of oxygen. And the delta H for this next reaction is going to go ahead and be negative 572 kilojoules. So this is a synthesis reaction. So we're beginning with 2 moles of hydrogen and 1 mole of oxygen, and we're forming 2 moles of water. Now, the difference here is our sign. So let's review our sign. So in this first reaction, we have a positive 572 kilojoules. So that means that this is endothermic. So in this one, it's going to be endo because it's positive. Now, in this one here in the bottom, it's negative, so this has to be exo. So we learned about this already. It's exothermic, so it's releasing heat. The top one is absorbing heat. Now, what I wanted to point out here was notice that the magnitudes are the same. It's just the sign that changes. Okay, so if you see a reaction written like this, you can easily tell if it's endo or exo just by knowing the sign. Now, let's talk about the magnitude a little bit. So the magnitude, our delta H, is proportional to the amount of substances the amount of substance we have in the reaction. So I'm going to compare these two. So it's the same reaction, but if you notice in this one here, it is all just divided by 2. So all the coefficients are halved, right? So if that's halved, we can still use this delta H here, but what are we going to have to do to this one? We are going to take half that amount. So half that amount would be our half times our negative 572 kilojoules. And here we're going to get a negative 286 kilojoules. So again, the relationship is that your enthalpy is proportional to the amount of substance in our reaction. And notice here, you guys are going to start to see some fractional coefficients, which we haven't seen a lot of in the past. So let's take a look at an example, mostly aluminum oxide. And it's a thermal decomposition, and we can represent it like this. Now, what we're going to try to do here is we're noticing our delta H. So that's a positive, so that must mean that this is an endothermic reaction. All right, so that's good to know. And what we want to know is if aluminum is produced this way, how many grams of aluminum, so we need to find grams of aluminum can form when we have this much heat being transferred. So we've got 1 times 10 to the 3 kilojoules of heat being transferred. So what we're going to do is we're going to start using our delta H of reaction as a conversion factor with the amount of moles. So we want to figure out the relationship, because we want aluminum. What's our relationship between aluminum and delta H? Well, we know we've got 2 moles of aluminum from our equation, and we know in 2 moles of aluminum we've got 1,676 kilojoules. So we can use these as conversion factors for our stoichiometry. I might as well finish that, conversion factors. So let's go ahead and set it up. So if that's a conversion factor, we don't start with that, right? We start with the number by itself. So we have 1 times 10 to the 3 kilojoules. And now we know that there's 1,676 kilojoules in 2 moles of aluminum. So if we were going to try to find oxygen, it would be 3/2 oxygen here per 1,676. If we wanted aluminum oxide, it would be this value again, 1,676 to 1 mole of aluminum oxide. But we care about aluminum, so we're going to use that coefficient. And now we know we want to find grams. Well, we can simply use the molar mass. In 1 mole of aluminum, we have 26.98 grams of aluminum. So we get a total of 32.20 grams of aluminum. Now let's look at sig figs here. So we've got 4, 4, 4, so 4 is good. Okay, so that's one example. Now let's look at another example. How much heat is associated with the complete combustion of a kilogram of sucrose? So this is just going in the opposite direction. Now our delta H again, it says complete combustion. So we have to know something about combustion. So combustion reactions are exothermic. So let's not forget the type of reactions we learned before. So combustion reactions are exothermic. They release heat. So we know this delta H has to be negative. So we have a delta H equal to negative 5.65 times 10 to the 3 kilojoules. Okay, so then we know we can have, we're going to start with our 1 kilograms of our sucrose. So C12H22O11. And then let's go ahead and take a look at how we can go from mass to our energy. So here we've got in a kilogram, 1,000 grams. So we have to know that conversion, which we know pretty well by now. And then what's the association with our delta H here? So we have the complete combustion. So that means in 1 mole of our sucrose, C12, I'm running out of room here, H22O11, that's going to be related to our negative 5.65 times 10 to the 3 kilojoules. So that's going to be the conversion factor that we're going to use. But how do we get from grams to our moles? So we're going to use the molar mass. There's 342.3 grams of our sucrose in 1 mole of sucrose, C12H22O11. And now we can cancel our grams and our kilograms, and now we can use our conversion factor. So in 1 mole of C12H22O11, we have negative 5.65 times 10 to the 3 kilojoules. So now our moles will cancel, and we're left with kilojoules. So we're left with negative 1.65 times 10 to the 4 kilojoules. There we go. Okay, so that's the end of this module using stoichiometry, getting the conversion factor, and solving for our delta H. Okay.